So now we are going to discuss in the module 8 projections of solids. So first, what is a solid? It is a three-dimensional object. So far we have seen the projections of a dimensionless object, that is a point. Then we have seen one-dimensional object, that is a straight line. Then two-dimensional objects, that is plane surfaces, circle, triangle, pentagon, etc. Now we are going to take up three-dimensional objects. So what are the? These are the various types of solids. You can see from this figure: sphere, cube, cuboid, cone, cylinder, square based pyramid, triangular based pyramid, triangular prism, hexagonal prism. So they will have all three dimensions. Height also will come, not only length and breadth, but height also will be there. So these are other type of solids. They are called polyhedrons. See here, identical. You take any face, they are symmetric, identical. We will discuss in detail again polyhedrons. These are special type of solids. This is one of the polyhedron, that is tetrahedron. See, there are total 4 faces, all the 4 are identical. That is why it is called tetra. Now you must have seen these pyramids in Egypt. Okay, so now let us see the first, before we discuss the projections of solids, some terminology one should know. So what are the, for prisms, let us take for prisms. See here you find triangular prism, square prism, hexagonal prism and cylinder. See, they are named depending upon their base. So what is a base? See, these are the bases, you can say represented by number 1. So these prisms will have 2 bases, one at the top and one below, bottom. So if the base is a triangular, it is a triangular prism. If it is square, it is a square prism. If it is a hexagonal, it is a hexagonal prism. So base. Next, the 2 bases are joined by verticals. They are called vertical edges. They are called vertical edges. And the center of the 2 bases, imaginary line passing through the center of the 2 bases are called axis, represented by 2. So, and then faces. What is meant by face? Each face will have, is like a rectangle with 2 base edges and with 2 vertical edges. You can see there will be 3 faces for a triangular prism, 4 for a square prism, 6 for hexagonal, like that. So face is a face, a plane surface like a rectangle having 2 base edges and 2 vertical edges, and the distance between the 2 bases is called the height. So if you look at the pyramids, the difference between the prisms and the pyramids is there will be only one base in the pyramids, and there is another sharp edge on the other side. It is called as an apex, see, indicated by 3. So one is again base as in the prisms, and 2 is a face. Here faces are like isosceles triangles, not as rectangles as seen in the prisms. So each is a isosceles triangle. So the apex, if you join to the various corners of the base, they are called slant edges. The lines joining the apex and the base are called slant edges. So each face will have 2 slant edges, 1 base edge. So this is the one should remember. So as I told you, we have seen the color pictures, polyhedrons. So these are solids, no doubt. They are the first one is a pyramid, another one is a cube, there is a prism, the other one is a combined two square pyramids connected base to base. The fourth one is sphere. See, you cannot differentiate between base and face. That is the speciality of these polyhedrons. There is no difference between base and the face. So if you look at the tetrahedron, the face and base are identical. Similarly, cube, face and base are identical. So that is the speciality of these polyhedrons. Solids of revolutions. These are obtained by a rotation of a plane surface. So if you rotate the rectangle about the axis shown, you will get a cylinder. Similarly, if you rotate a right angle triangle, you will get a cone, and if you rotate a semicircle, you will get a sphere. These are called solids of revolution. Now, classification of problems in the projections of solids. How the various problems, that is projections of solids, are classified based on the axis. How the axis of the solid is. So, axis is nothing but an imaginary line. So, if that is parallel to both, I mean first case not parallel to both, like in the straight lines, here it should be parallel to one plane, perpendicular to the other. That is the simple position. Second one is axis inclined to one and parallel to the other, and axis parallel to both and axis inclined to both. So this is how the order in which one has to attempt the various problems on the projections of solids. So axis perpendicular to one and parallel to the other. So let us see, two prisms are taken. One is a triangular prism, another is a hexagonal prism. How are these two prisms? If you look at this first one, triangular prism, axis of the prism is perpendicular to HP, and parallel to VP. Whereas if you look at this, axis is perpendicular to VP and parallel to HP. So that is the in both the cases, axis is perpendicular to one, parallel to the other. So if you see this, first the axis is perpendicular to HP in the triangular prism. So if you look from the top, you will see the base. So first you have to start with the drawing of construction of the base in the top view, and then from this you project upwards to get the front view. So similarly here, because the axis is perpendicular to VP, you see the base in the front view. So you start with the front view by drawing the hexagon as shown, and then from project downwards to get the top view. So one should start with either top view or front view wherever you see the base. So start with the base. If it is visible in the top view, you start from the top view. If it is visible in the front view, you start from the front view. So first base will be visible. Now axis perpendicular to VP, so the same thing is explained here. Now look at the same two different pyramids. We have seen previously two different prisms. Here two different pyramids. So what is the first pyramid? It is a triangular pyramid. And how is it? The axis is perpendicular to HP, parallel to VP. Now if you look at the hexagonal pyramid, the axis is parallel to HP, perpendicular to VP. So as I told you, you start with the top view. You draw the top view of the triangular pyramid, that is a equilateral triangle, and you locate the center, you name it as O, and then you join O1, O2, O3, because these are the slant edges. So slant edges are visible if you see from the top. If you don't locate O and join to where it 1, 2, 3, it represents a prism. So the difference between the top view of a prism or a pyramid, that is, you will see the apex and the slant edges in the pyramid, whereas in the prism you will not see. So here in this figure you start with the front view, you draw the hexagon in the front view, again find the center, you join to all the 6 points and you will get the front view. From that you project downwards, you will get the top view. So coming next step is axis is inclined to one and parallel to the other. So this type of problems you have to start first assuming the angle as axis angle as 90 degrees, that is perpendicular. So that means we are converting the given problem into first simple position. So here a cylinder problem is explained. You can see the cylinder, the axis is parallel to VP and inclined at 60 degrees. So one should first assume the 60 degrees as 90. That means axis is perpendicular to HP and parallel to VP. So you will see the in the top view as a circle, in the front view it looks like a rectangle. So we are converting the given position into simple position, right? Next what we are doing next, you take the front view with the axis you inclined at 60 degrees, you draw the front view. That means you rotate the front view about 3 dash such that the axis makes 60 degrees, and now you project from the top view and you draw horizontals from the previous top view, you will get the final top view. See, you look here, two bases are visible. So visible lines you draw by full lines, we are not visible by dotted. So the various steps are given. Now here this is a case axis inclined to VP, and that means axis is this is another problem. Axis inclined, a cone is taken here. If you look at this, axis is inclined to VP, parallel to HP. Previously it is a cylinder problem, axis is inclined to HP, parallel to VP. Here it is parallel to HP, inclined to VP. So this is how this cone is. It is touching, lying on the VP on one of its generators, that is 01. 01 generator is on the VP. So first you take the base as in the VP, and then you get this, that is the simple position. From this simple position you turn the top view such that 01 comes onto the XY line, and from here you get the front view. So this is how you get the for the required position, that is axis inclined to VP indirectly given. This is an indirect problem. Axis is inclined to VP is given by way of saying one generator is on the VP. So this is what is an auxiliary plane. You must have, in the module 7 we have discussed the auxiliary plane method. So this is applied for the projections of solids, and unless you go by this method you will not be able to save time. So here same problems we discussed previously are being repeated using the auxiliary plane method. See here, first as usual you will draw the projections of the cylinder, simple axis perpendicular to HP, parallel to VP. Now axis inclined means we did previously, turn the front view. Now instead of turning the front view, this XY line is turned from XY to X1, Y1, and now with respect to this X1, Y1 the axis is inclined. Now you project onto the X1, Y1 and extend and mark the same distances from XY. You take the same distances from XY, and mark from x1, y1, you will get the new top view corresponding to inclined axis. So here this is the use of auxiliary plane method. Same thing, cone problem. So instead of 2 front views and 2 top views, you will get here with 3 figures. One common top view is common, and to get 2 different front views, simple front view and actual front view. So this the application of the auxiliary plane method. Now coming to axis parallel to both HP and VP. This is not a simple case as in the case of straight lines. Axis parallel to both means this is the final front view and top view. Axis parallel means you will not see the base. Therefore, how to start the problem projections? So first you assume the axis as perpendicular to 1, that is simple position. So here it is assumed as axis perpendicular to VP and parallel to HP, and corresponding front view and top view is drawn first. So it is first converted into a simple problem by making it parallel to HP and perpendicular to VP. Afterwards, this top view is turned by 90 degrees, and then from this you will get the final position of the front view. So this is how you have to take up when the solid axis is parallel to both. Same thing using auxiliary plane method. So in this again, first simple position, then x1, y1 is taken perpendicular to xy as shown, and then it is projected to get the final front view. So this simplifies. With a common top view, you get the 2 front views. So this is now finally axis inclined to both. So if you look at this, this is a tetrahedron. That means it is nothing but a triangular pyramid. So here, how is this problem? First, the problem is given, the axis is inclined to both, maybe given 2 different angles or one angle directly given, another angle indirectly mentioned. Here this is the simple position with one edge of the base perpendicular to VP. So this is the front view, this is the top view. Next, the one face is perpendicular to HP. One face is perpendicular to HP. So here in the simple position it is inclined. 0, 1 dash, 0 dash, 1 dash, 2 dash is inclined. It is to be made perpendicular. So you rotate about 1 dash, 2 dash in the front view and make this 1 dash, 0 dash, 1 dash, 2 dash perpendicular to XY. The corresponding top view is this. Next, this face which is perpendicular to HP, perpendicular to both HP and VP. Now it should be inclined to VP at the given angle. So you turn this top view to this required angle and project upwards, you will get the final front view. So here the axis inclinations are given indirectly by way of saying one face is perpendicular to HP and inclined to VP. So this is one standard problem. The procedure is explained, and the same problem has been done using auxiliary plane method. So first you attempt in the step by step method, then you apply the auxiliary plane method, then you will see the advantage of this method. Next, let us take a cube, a problem on cube. What is a solid diagonal? What is a face diagonal? If you look at this, this is a cube problem. See, each face will have a diagonal, that is called a face diagonal. But across the solid, if you take two opposite corners, say here C dash and here A dash, top C dash, bottom A dash, E dash. So this if you join, that is called a solid diagonal, that goes across the solid. These are called solid diagonal. So how is this cube? Cube, we have to draw the projections of the cube. The cube is like this. The solid diagonal is parallel to HP, perpendicular to VP. That means the cube is resting on a corner. So how to start this problem? First you have to start in this way, simple position, with faces equally inclined. So you start draw a square such that they are inclined at 45 degrees to XY line. Next, after drawing this top view, you project upwards, mark the height equal to the side of the base, and you will get the simple elevation. Next, you draw a light line connecting the solid diagonal to represent the solid diagonal. Suppose say we have selected this. Then you drop a perpendicular from G dash onto this, and next what you do is you rotate this front view such that this normal drawn onto the solid diagonal is perpendicular. So whatever length this is, G dash, P dash, you mark here, draw a perpendicular, mark this length, then you draw horizontal, and then you mark length P dash, E dash and P dash, these points, you locate C dash, and then you complete the front view. Afterwards you get the corresponding top view. This top view here, solid diagonal is parallel to both, but it should be perpendicular to VP, parallel to HP. Therefore this top view you turn by 90 degrees, same thing you have to turn by 90 degrees, and then project upwards. You will get the front view, that is ultimately the final front view, which is corresponding to solid diagonal parallel to one, perpendicular to the other. So you have to go by step like this. So detailed procedure is explained, and this is a very important example which will be again discussed in the coming modules, that is on isometric projections. Again it's the same thing explained by using auxiliary plane methods. So here one auxiliary plane is taken x1, y1 perpendicular to the solid diagonal directly, and it is projected here by keeping the same distances. You take the top view distances of 1, 2, 3, 4 and mark on the corresponding projectors. So directly you will get this. So it will give directly the final front view. So projections of spheres. So what is a sphere? Sphere, as you know, say take a ball or earth, they are all spherical. So every sphere will have a center. It's named by C dash, and if it is resting on the HP, it will be touching. So it will be touching at point P. So in the front view you call it P dash and top view P. So you look at, both are circles. The top view looks like a circle, front view looks like a circle, but the naming, how the center is named, or where is the point of contact, that tells whether it is a front view or a top view. So this is how C and P will be at the center in the top view, they are at a distance in the front view. Now there are three cases, two identical spheres, one over the other, one behind the other, one by the side are shown. So this how the centers and points of contacts are, point of contact between the spheres is indicated by Q dash. Point of contact with the ground is indicated by P1, P2 dash. So if you look at the other figure, they are unequal spheres. One is smaller, another is bigger. Same cases, one over the other, one behind the other, one by the side. So if problems on spheres, before you deal, this one should understand. Now let us see this problem. There are 4 equal spheres resting on the ground. A 5th sphere is placed centrally on that, and you are asked to determine the height of the 5th sphere. So first you should imagine the centers of the 5 spheres, and if you imagine the lines joining the centers of the 5 spheres, it is nothing but a square pyramid. So 4 base circles, spheres will give you the base, and the upper one if you join slant edges. So just like a pyramid, if you imagine the lines joining these centers of the spheres, it is nothing but a square pyramid. So first you take in the simple position, that is the line joining the centers of the base spheres as inclined at 45 degrees. You will get this, because the center distance between C1 and C5 will be having true length. Therefore, from here C4 dash or C1 dash, C2 dash, you take radius equal to sum of the radii, and you will get the center of the C5 dash. So that after getting, then you turn this to this position, that is line joining the centers of the 2 base spheres is 30 degrees. So heights will not change. So you can take the height of the 5th sphere same as in the previous case, and how they look in the front view. The spheres which are visible you show by full line and not visible by dotted. So it's just spheres problem, but you can imagine as a pyramid problem. So like that various steps are indicated. Okay, thank you.